we can also project a point onto an axis, right? And the dot product is also very useful when we want to project a point on the axis, and meaning that if you want to find out that what is the shadow, if, or you can say what is the component of that point is onto that particular axis, we can use the projection like this. All you have to do is compute the dot product divided by the mod. Okay, and then multiply. Okay, so I'll tell you. So we have got u dot v divided by mod, or the easiest way to understand is that first of all, whatever axis it is, we basically compute that unit vector of that axis. So here, the projection of vector v onto axis u, let's say there is axis u. A question from Robert is, what if u and v is a pandas data frame? Does it work the same? Not really. All these operations are not available on pandas data frame. That's why whenever we are doing linear algebra or any mathematical computation, we prefer to use Numpy. Okay, we use Numpy because pandas data frame could have all kinds of data in it, and that's why. Okay. All right. So if we have a point like this and there's an axis going like this, the way we compute its projection is by, first of all, computing the, let's say this is u, this is v. So we say, okay, and we say u dot v divided by unit vector u and multiplied by u and something on this sort. Okay, because the direction of final value is same as the direction of u. Okay, so this is called the projection. Projection is you essentially compute the dot product and multiply by the axis in which we are trying to find the projection, and then divide by u square. Or you can say that whatever axis it is, you compute the unit vector. So, and using this, we first compute the angle or the impact of v onto this particular unit vector, and then we give it a direction using this. Okay, so the projection will be in this direction, because dot product always gives us a single value, always gives us a scalar instead of a vector, right? So this will be a scalar and this will be a vector, right? So scalar multiplied by a vector is a vector, meaning it has a direction and it has a magnitude. All right, it could be in 3 dimension, it could be in 4 dimension, and so on. All right, so that's how you can visualize the projection. Say, for example, there is this, right? There's this. We are finding the projection of this one onto this particular vector, and this is that particular value. Okay, so all we did was, so if we take this vector and compute the u cos theta, right? We compute the dot product, then we get a scalar value. Now, if we multiply by a unit vector, we get a direction as well, right? So this is the projection of this onto this, right? This vector that you see from here to here, this is the projection of this vector onto this vector. Okay, is the projection clear to everybody? All you need to do is first, let's say this is your u, this is your v. Now compute the unit vector of the u, do a dot product of v and u, and then multiply with a unit vector u. Okay, question from Manoj is, projection will depend upon which point we are viewing, isn't it? Yes. So right. So the projection of this vector onto this is going to be different than this. Okay. So let me put it this way. Okay. All right. The way we are defining projection, let's say this is our U, this is our V. Okay. This is U, this is our V, right? So projection of U onto V is this. And how much is that? We basically say V dot U, okay? V dot U, all right. So we say U dot V unit vector, meaning first of all, compute the unit vector of this one by dividing its magnitude, and then we multiply it with unit vector, right? Similarly here, when we take this and we want to find out the projection of this one onto this, will basically it'll be this value. Okay, how much is that? V dot U, right? And this is a unit vector, okay, and multiplied with, okay, so this is the projection of V on U and U on V. Yes, this downward vertical line, this is perpendicular to this. Okay. If you remember the trigonometry, all we are doing is U cos theta, and then we are giving it a direction. Okay. Similarly, we are saying V cos theta, right, and giving it a direction. Right. So projecting is like if there was sun on the top, exactly on the top, what is the shadow are we casting? Yes, we are projecting one vector onto another. So we are throwing a light on this object, okay, from here, and we're projecting this object onto this curtain, right? So we're basically projecting, we're throwing a light on this, we're throwing a light on this perpendicular to this axis, this is the curtain, and we're projecting this point onto the curtain, if you think of it this way. All right, wonderful. Wonderful. And interestingly, I found that the idea of projection is actually not clear to many. Okay, and just that the who is projecting where, that there is always this confusion. Okay, the way you can think of it is in terms of throwing a light and a curtain. Okay, all right, so a matrix, similarly, the way we have learned about vectors, a matrix is a rectangular array of scalars like this, right? It could be three-dimensional, it could be four-dimensional, it could be many-dimensional. Okay, and matrices are very, very powerful, and they help us in representing and performing linear transformations such as rotation, translation, and scaling. Okay. A question from Deepak is how projections are used in machine learning. I mean use case. All right, wonderful question. Okay. I should I take a bit of digression? I hope that'll. Okay. Go ahead, Satyajit. Yes. Yes. Okay. All right. So I will take one more example, Satyajit. Okay. I will take one more example. Right. All right. So here we go. Imagine that we had a three-dimensional space. Okay. Or we can say all right. Imagine that we have a three-dimensional space, right? Let me just try to plot it in some way. Okay. And we have, oh, this doesn't look great. Okay. So I think this will be better. All right. Now, think of it this way that we have, let's say, right? So if you see that even though the data is in the three-dimensional space, right? It's actually very straight line, right? And unnecessarily, we are each of these data sets, right? This is having XYZ three components, and so on, right? So even though this data set looks like it's in three-dimensional, but it's actually not really that three-dimensional, right? It is like that. So what we do in these cases is we come up with a plane, right? And project these dots on that plane. Okay. So what we do is we eliminate one of the axes, okay, and we keep only these the this side. Okay. So essentially, what we are trying to do is we are eliminating one of the dimensions of each of them. We are removing z-axis. We are removing z-axis in favor of keeping only x and y, right? Because the more number of x's you have, the more memory system will take, and there are far more complexities. We will learn as part of dimensionality reduction in one of the sections that once we have figured out that what could be that plane that would be, that could go through nearby this data. Once we have decided upon that, then what we do is we take each of these points and project it. So and project it onto that plane, and on that plane basically we get the shadow of these data points, which is very similar to what the behavior is, and hence, okay. Now another way of looking at it is, okay, all right, who will tell me that do we convert a 3D object into 2D as per our day-to-day routine? Yes, anyone? Perfect. Perfect. So yes, camera is one such thing. We take a photo, we convert a 3D object into a 2D, right? And what's actually happening in case of camera? Um, why do we point the camera in such a way? Okay, that's going to be a little bit. So all we are trying to do is when we are saying projecting here also, we are moving the camera in such a way that we cover all the data points. Okay. So when we are taking the photo, what's happening is each of the points on the faces of people or in the view is being projected onto the film. That's the real meaning of projecting. In machine learning, you will see that what we will do is when we do the dimensionality reduction the way we do in the case of photos, when we are taking photo, what we are doing is we are eliminating one dimension called z-axis. So we are moving the camera in such a way that we cover the maximum information, we cover the maximum information in the view, and we eliminate the third dimension, right? That's what is taking the photo means. If you are a great, I mean, I the more information you capture in a photo, the better the photo comes out to be. And that's why we move the camera. We don't take the photo from the side of everybody. We don't take the photo from the top, uh, because it'll only show the heads. It won't show the information like faces, which are very important. And so the same thing we do in case of machine learning. What we do is we we let's say we have this data set. We will come up with a plane or an axis from which we can take the snapshot of this data and still remove one of the axes, right? Right. And that's what we will do in case of machine learning. Why? Because more number of dimensions are really dangerous. And if you have a million dimension, you will have to come up with lesser dimension. And that's what is all dimensionality reduction chapter is about. Okay. So to remove the dimensions, we find the angle of projection which is basically we find out that that particular plane of projection which gives us the maximum variance, maximum information, and then we do the projection, and that's where the projections are used in machine learning. Okay, good question. I hope I was able to answer your question. Good question. So how do we find out the plane points close to which plane? Yes, we will discuss an algorithm called principal component. We will discuss what do you call, using SVD and so on. Um, we will explain how to find out that plane which has the maximum variance. Okay. So generally we do the way we find out that plane in which we need to project is the one which captures the maximum information as opposed to the one. If we basically project it on something like this, imagine this. So everything will, if you throw the torch, the light from this side, everything will be just a dot, right? Therefore, it's not really useful. So if we have to take the photo of these dots and they are all in a single line, and if we are taking from the photo this from this side or projecting from this side onto this film, will be a single dot and we lose so much information. Okay, so we generally find that particular plane on which we have the maximum variance. All right, so great question. And all right, so moving ahead, right? So matrices in Python, we have, okay, we have two-dimensional matrix like this, and basically you can think of them as, you know, composed of many vectors, and vectors were only single dimension. The matrices are multiple dimensions. So this is our matrix, and okay, we have not yet defined it. All right, so when we create a array like this which is 2 by 3, so this number of dimensions are 2, and the more important information is a dot shape. Okay, so the shape of this is 2 by 3, right? 2 rows and 3 columns. Okay, and yes, size means how many elements are there. The elements are indexed from here to there. This is called 0, 0. This is called 1, 1. Though in the classical mathematical terms, we started with 1, 1 and 1, 2, 1, 3, 1, n. But in case of the computing, we start with 0, 0, 0, 1, 0, 2, 0, 3, and so on. Specifically in Python and C and other similar programming language, we start with 0, 0, and so on. But when we talk about maths, when we use this right? When we use Numpy or Python or C or Java, we start with 0, 0. Okay, this is the way we classically represented maths. Okay, here notice that we are increasing the first value, right? That's the row, and not increasing. If you're going column wise, this one is increasing the first value. If you're going row wise, the second value is increasing. All right, so that's how we represent a matrix, and matrix is again is a NumPy array. Okay, matrix again is a NumPy array, and we can access columns and rows like this. So here we are saying that give me all elements in the rows. Colon means give me all elements, right? The colon basically is for slicing the array, saying that give me from range at this point to this point. Here we are saying give me all rows and first column. right? First column is this one. This is zeroth column. This is first column. This is second column, right? So we are saying that give me the column one, right? If you want to say that give me the first row, right, and all columns, that means give me 40, 50, and 60, right? And if you want to access a particular element like 1 comma 2, 1 comma 2, that is 60, so we can access that. Moving ahead, so right, we have already discussed these parts. So if you want to access saying that give me all rows and columns only from 2 to 3, right, we can do that. Okay, 2 to 3 is nothing but starting at 2, ending at 3, ending before 3. Okay, that means only the second column. Okay, now when we talk about matrices, there is a square matrix. A square matrix is the one in which the rows and columns are equal. Okay, the upper triangular matrix is the one in which these everything below the diagonal towards the left, everything below the diagonal towards the left is 0. Okay, similarly, this is lower triangular matrix in which the upper side towards the right is 0 beyond the diagonal. Of course, these values could also be 0, but when we say that this is lower triangular matrix, this must be 0. Okay, so triangular matrix is either lower or upper. That's called triangle. You can create a diagonal matrix. A diagonal matrix is the one that only has values on the diagonal, and we can create the diagonal matrix using diag function of Numpy. Okay, a question from Deepak is, in a machine learning problem, when we go for 1D array, all right, a question from Deepak is, when do we go for 1D array and when do we go for 2D array? Is it based on how many objects are we representing? I mean, two objects comparison, 1D array and multiple object comparison, 2D matrix. So it all depends on the problem statement, right? So like for example, when let's say it all depends on what we are trying to do, right? When we said that we are trying to solve a equation like sequence of equation, right? And all right, so where did it go? Okay, yeah. So this is when let's say this is our equations. It has some columns and some rows. This is represented generally as a 2D array, while this is represented as 1D array, and so on, right? So if we have more number of columns here, it will still remain as 2D array. If we have more number of equations here, still it will remain as 2D array. Okay, a question from Deepak is, I mean, solving as vectors versus solving as data frame. Okay, so question is that when do we use 2D array and when do we use a pandas data frame, right? Is that the question? I see. So yes. Okay, okay. So it all depends on what is it that we are trying to solve. Okay, it varies from context to context. Say for example, we are in this equation itself, if you see, take a look at this one. So we have this equation, these sequence of equations, right? And we have rows and columns. So this part we will be representing as 2D array, while this part is 1D array, right? This is 2D array. So it's the problem statement which will dictate whether it's a 2D array or 1D array. We generally don't have to do that. Also, imagine that we have an algorithm which solves such kind of data. So the way we think of algorithm is that this is our X, this is our Y, and basically if we feed this X into, sorry, okay. So imagine that this is our machine learning algorithm, and this is our X, this is our Y. We will feed X and Y to this machine learning model, and we will get kind of another 2D array representing model. Okay. So there is no thumb rule as such when to go for 1D or 2D. It varies from the problem to problem statement. Also, it varies from which algorithm are we going to use. Okay. So if we are, say, using convolutional neural network, as we learn later, there could be 4D arrays. If we are trying to solve something using linear regression, it'll be mostly 2D arrays, which we'll be feeding to the model and so on. Okay. Yes, we have objects and features list, then when to solve them as vectors, when to solve them using 2D array, data frame. Yes, it's a little early for that. We'll learn that part soon enough. For now, you can take an analogy of, the features like this. These are features and this is the predicted value. And that's the way you can think of it. So we'll be using for features, we'll be using a 2D array. For the predictions, we'll be using the one-dimensional array. Okay. All right. But it won't be too much of a difference, don't worry, because we can quickly convert 2D array into 1D and 1D to 2D, and we'll do that. All right, so we can create a diagonal matrix like this, and okay. Okay, we can pick using the diag function, this one. We can also, given a matrix, it can also give us the diagonal. Okay, 1, 5, 9. Now there is something called identity matrix. Identity matrix is a diagonal matrix with everything as 1, like this. You see, 1, 1, 1, everything is 0. This is basically the diagonal matrix. And you can create a diagonal matrix, identity matrix, using np.eye function, I function. All right. We can add matrix just like this. If we have Q and R, we can add the corresponding element with corresponding value, right? That's called adding matrices. So if we have A like this and B like this, so we can say A plus B and we'll get these values like this. So 10 got added to 1, 20 got added to 2, and so on, right? Addition is commutative, meaning if you change the order, the answer is same. Okay. And the addition is also associative, meaning that if we say A plus B plus C, the answer will be like this. Okay. So even if we put the brackets at different places, answer will be different. Or sorry, answer will be same. It won't be changing. So the addition is associative as well as commutative. No matter where we put the brackets, we'll get the same answer. We can multiply a scalar. We can multiply the whole matrix with a scalar. Okay. Like this. If you multiply with a scalar, we get this. Okay. So in case you have to multiply the whole matrix with the same number, you don't have to write 2 for loops. You can just use the normal multiplication. All right. So again, This multiplication is scalar multiplication is commutative and associative, as well as distributive, because 2 into a plus b is same as 2 into a plus 2 into b. Okay, so that's basic operations on matrix. Now here is a very important aspect. So far, matrix operation have been mostly intuitive, but multiplying matrices is far more involved. A matrix Q of size m into n can be multiplied by another matrix of size r, sorry, another matrix r of the size n into q, and the matrix multiplication is generally represented like q and r without the multiplication sign or dot. The result P is a matrix of size m by q. If q is m by n and r is n by q, right? The P, which is q and r multiplied, will be m and q. Also notice that this n is same here and here, right? So number of columns in first matrix is same as number of rows in second one. Okay, and when they get multiplied, this r disappears and we are left with m and q, right? That's why P is a m and q matrix where each element is computed as sum of the products. Okay, so again, the way you can visualize, or the way you can find utility is by thinking of it this way, that here this is a matrix and this is a kind of a matrix with 2 by 1. Here what we are doing is what is the size of this one? This one is 2 by 2 and this one is 2 by 1, correct? So you can see these two are same. And basically the matrix representation, like the multiplication actually came from, this representation actually came from solving multiple equations parallelly and representing that as a matrix. Okay, that's where the whole that's where this multiplication comes from. Okay, so let's take a look at this one. So here what we are trying to do is we are saying 10, 20, 30. So this is A and D. A is this and D is this, right? So we are saying 10, 20, 30 multiply with 10 multiplied by 2, 20 multiplied by 11, 30 multiplied by 23. So we are taking the row, multiplying with column, right? So 10 with 2, 20 with 11, 30 with 23, and then we sum up everything, right? If you take a look, this is how it looks like. So this is 930, right? This is 930. Similarly, we have another row, or we take the same row, multiply with this column, multiply each value with the corresponding one, and then sum it up, and then we get the results. Then we take another one, take this one, multiply here. Whatever is the resultant, we put it here, and so on. So this way, we can represent a matrix. We can utilize matrix to do many things. So such as multiplication. Multiplication, one of the significance you will see is with respect to having with respect to thinking in terms of multiple equations, and we are putting it that way. So, but there are quite a few more applications of matrix multiplication. All right. To achieve matrix multiplication, we use the dot product between the two. We say A dot D, and we get the same answer. Okay. You can see. So A is this, and D is this, right? And we are saying A dot D. we're getting this result. So the way we multiply matrix is using the same dot method that we used for vectors. Okay. All right. So this way. All right. Please notice that this one is not so intuitive, right? One of the things that you'll notice is that if we can multiply A with D like this, if we can multiply A and D like this, we can't really multiply D and A. Okay, why? Because number of columns in the first one must be same as number of rows in the second one, right? So if we had the other way, okay, if we had the other way, as in D multiplied by A, how many columns does it have? It has 4 columns, while this one has how many rows? 2 rows. And therefore, multiplying this with this is doing D dot A is not possible. Okay, D dot A is not possible. So you can see D dot A is not really possible. Is it clear why it's not possible? The col the columns of the first one must be same as the row of the second one. Only then we'll be able to multiply, right? So in fact, right? So matrix multiplication is not commutative in general. QR is not equal to RQ, right? In fact, QR and RQ are both defined if Q has a size of m by n and R has a size of n by m. Let's look at an example where both are defined and show that they are not equal, right? They are not equal. So we have F. So, okay. So even if we are able to multiply, right? Even then, both are not equal. The F dot A and F dot A dot F and F dot A is not equal. So you can see clearly that when we are doing A dot F, we are getting this matrix, and when we are doing F dot A, we're getting this matrix. All right. So on the other hand, the matrix multiplications are associative, meaning if we do A dot D dot G, right, or we do A dot and D dot G, okay, then also the answer is same. All right. So matrix multiplications are distributed over addition. As in, this is not going to be too useful, but at a couple of points, then when we will talk about gradient descent, this will come into the picture. Okay. So when we have, let's say, two matrices A and B here, and we are saying dot D, it essentially means that it essentially is equal to this one. So this is distributive over addition, and the order in which we do the dot product is also changeable, meaning we can put, it's basically associative. Okay, we can put the brackets here, meaning QRS is equal to QR and S, right? Q multiplied by RS. So here we are multiplying R and S first, then here we are multiplying Q and R first. Okay, so that's the associativeness. The product of matrix by an identity matrix results in the same matrix M. More formally, if M is a M by N matrix, then MI Okay, mi should be equal to I into m, and that should be equal to 1. Let's take a look at. So this is, let's say this is the matrix that we are talking about, and here is 3 by 3 matrix. So here we are saying a dot np dot I, right? This one, this is identity matrix. So you can take a look at a value again. All right, let me just restart. All right, so basically when we multiply a matrix with the identity matrix, it's all the same. It remains the same. The resultant is the same actual matrix, right? So let's say we have A like this, and we are doing the dot product with this. This is an identity matrix. The the resultant is same, right? The resultant is same, and yeah. And similarly, if we are multiplying a matrix, the identity matrix with A, the result is again A. Notice that here we created an identity matrix of 3 values, while here we created an identity matrix of 2 values. Okay, why? Because the number of rows in this matrix must be same as the number of rows in A, right? In this matrix. So that's the reason why we have here we have created an identity matrix of 3, and here we have 1. Wonderful. So, all right, is everybody with me so far? Now, please note that NumPy, if you do instead of dot product, if we see asterisk, it's basically element-wise multiplication. It's not. It's not the kind of metric, the kind of multiplication that we just did. While the NumPy provides the operator called at, which basically multiplies the matrices, right? There's the dot product. Now, we can do the transpose of a matrix using NumPy methods. It's actually pretty straightforward. So we can always say a matrix dot T to transpose. What is transpose? Rows becomes column and column becomes row, right? So 10, 20, 30, instead of being a row, it becomes column. 40, 50, 60 becomes the second column instead of being second row. Okay. So we convert each row into a column. So this is a dot t, so you can see the difference. And you can see that if we do the transpose twice, it's equal to a. It becomes original one. The transpose is again distributive, meaning the either you add first or transpose later, or first transpose and then add. The resultant is same. Okay. Also note that when we are doing transpose in case of dot product, so q dot r, the transpose of it is same as the dot product of d, the transpose of d dot transpose of a. Notice that the order is reversed. The order is reversed, right? All right. So converting 1D array into 2D, we can use the mechanisms to do that. This is a common need. Okay, so converting a 2D array into 1D is very much possible. We can do reshape, and similarly we could do the reshape in case of converting 1D into 2D. Okay, so this we have already discussed as part of NumPy, and here we go. Okay, so you can see here. Now notice a couple of things. All right, let's say we had this. Okay, all we want to do is we want to convert it into 2D array such that there is one extra bracket around it, right? Meaning it'll have only one row and that becomes this one, right? All right. So one way is just put the round brackets around it and convert it into array. This is the first technique, right? And second way is we call this method. We say u and we add one more access saying np.new access and it will automatically add new access to it. Now you can see two brackets around it. Okay. Also, you could achieve the same thing using this. Okay. And notice that this will be very common. It will be very common to do convert 1D array into 2D. Okay. And this also does the same thing. This also achieves the same thing. And this also achieves the same. Now, the important part is that when we are doing the transpose, it comes like this. And if we, now I think you can find the difference between the two. So you can see here, this is our u, right? This is u. This is u dot transpose. Notice that in case of vector, transpose doesn't mean anything, right? What's vector? Vector is nothing, 1D array. And here you can see u and u dot t, that transpose is same thing. Okay. Now, why do we need to convert 1D array into 2D array? Good question. Good question. Why are we trying to do this? Imagine this, right? Imagine this here when we are operating on this, like these values 6 and 9, right? 6 and 9. Now 6 and 9 is going to be 6 comma 9, right? On the left hand side it's going to be a matrix. Now this wouldn't make much sense. Instead we need to convert it into a matrix such that it has only one column like this, right? Instead of like this, right? This is a 2D array. First column is only the one which is having some value. Therefore, we need to convert this into something like this, right? Do you get the difference? This one is a vector and this one is a 2D array, right? So how do we convert? And this, I mean, trust me on this, that this will be the common thing that you'll be doing when we are feeding data to algorithm. Probably you will never touch the algorithm underlying, but you will be basically spending more time on translating the accesses. Okay, so now notice that if it's a vector, then transport doesn't mean anything, so it would not work. Therefore, what you need to do is, first of all, convert it into 2D array. Convert it into 2D array by the methods that we discussed above, right? Like either using np access, np new access, np new access, then using putting brackets around it, and so on, right? So using that, you could convert that into a column. All right. So you can see that the shape of u was a vector 2 by nothing, and shape of this after converting into a matrix, the shape is 1 row and 2 columns, and the shape of A is 2 columns and 3 rows. Sorry, 2 rows and 3 columns. Okay. All right. So we can plot a matrix on. Okay, I'm just running everything. Right? So we can just plot the data from the matrix like this, right? Here it has 2 columns, two rows and so many columns, so many data points and 2 x and y, right? So we can plot it like that. Okay, and since in matrix the vectors are ordered, you can draw the path, and the path is represented by the connected dots. Okay, so so here this is the path. In case you change the order, the shape will change. Okay, and we can fill in the colors, and this is how we can also visualize the matrix. Okay, so there are lots of geometric applications of matrix. Can somebody name one quickly? Something that you do all the time on your phone. All right, the everything that you see on Instagram filters, it's basically the Instagram filters are nothing but matrix operations. All right, just that Instagram filters are far more humane than what we are talking, right? So everything that you see on Instagram, let's say you want to convert a photo into grayscale, that's basically extremely simple, computing all the values, average of a particular axis. Okay, you'll be amazed at that how simple all of that has become thanks to NumPy and the matrix operations. Okay, so there are lots of the main place where you will meddle with matrix is when you operate on videos, photos, or data in general. Let's say you want to compress a certain data. In that, you will also use matrix operations. Okay, video, for example, is nothing but yeah, is video is nothing but four-dimensional object. Okay, you can think of it that it contains matrix of multiple dimensions. Here it's 2 by 3, or here it's basically two-dimensional matrix, but matrix could be more than that. Okay, so coming back to it, here, all right. So here we're trying to visualize what happens when we add two matrices. Imagine we have P and H. So P is one, okay, let me go back. So P is this, P is one matrix, and H is this matrix. And the new value of this one, so what we did was we applied H. The matrix H is basically represented by so many vectors, and we are saying that okay, P was a shape, and we are saying P plus H. So it's essentially squeezing, or you can say, what do you say? We are deforming or changing the shape by the way of another matrix. Okay, so essentially by adding P and H, this is what is happening. That's how you can visualize. Okay, if this other matrix was full of identical vectors, this is what will happen. It'll be moving the shape from one point to another. Okay, all right. Now when we multiply a matrix by some scalar value, meaning a number, what happens? It basically zooms it out. Okay, it basically scales it out. That's all. Okay, that's how you can think of the multiplying by scalar. Now the Okay, so what's happening here is, let me just delete this part. Yeah, so we can imagine the matrix multiplication in the same way, the way we imagine the way we visualized the projection onto an axis. So let's take an example by defining a 1 by 2 matrix called U. This is where we have defined the matrix, right? This is basically a simple matrix, just that we put one more bracket around it, so it became a two-dimensional matrix. So this is just one horizontal vector, and this is another matrix. This is a proper matrix. This one is not really proper matrix, it's just a vector. So here when we say u dot p, meaning we are multiplying u and p using the dot product. Okay, that's what we're doing here. And then it's essentially projection. Okay, it's essentially projection. Right, now you can see. So where is our 0, 1? Okay, so u dot p is actually the other way. Here u dot p means we are projecting p onto u. We are projecting p onto u. So imagine that this is an axis, right? And this is our hues object. And when we are basically doing u dot p, right? This is our u, this is our p. What's happening is we are projecting on this axis. Now you can see clearly it's exactly like taking photo, right? Whatever is at this point becomes this, whatever is this point becomes this, whatever is this point becomes this. Imagine that we are standing this side with the camera, and whatever is happening from here, it's basically projecting on the camera's film, right? So essentially projection of a matrix onto a particular line or a plane is basically the dot product. Okay, I hope you are able to visualize what it means by dot product. Okay, so you can see 3, 3, 4, and 4.5, 3, 4, 4.6, and 1. 4, this is for 4.6 and 1. So that's after projection. Okay, so we have a shape which has got many coordinates, and basically this is matrix. This is one row, this is another row, this is another row, and this is another row. And when we are projecting, essentially it's basically just like taking photo. So dot product, you can think of it like projections. Okay, that's the easiest way to visualize it, easiest apart from the other. Okay, in the same way, we are projecting the other array, this one onto, here we are basically plotting the projections. You can see there is a method called plot projections that we have defined, and in that you just take a look at this code and you will get an idea as in what's going on. Okay, similarly we can project this shape onto another line which is at 30-degree angle. Okay, so this was matrix multiplication with a vector, which is essentially projecting a matrix onto a line or a plane. Okay, now let's create a 2 by 2 matrix containing two unit vectors that make 30-degree and 120-degree angles with the horizontal axis. Okay, and okay, yeah. So basically, the other things that you do in let's say in Photoshop or other tools essentially is basically again is achieved using matrix multiplication. So if you have an image like this and you want to rotate it at certain angle, what you do is you create another matrix containing the vectors of each of these angles, and then we rotate it. Okay, so all we need to do is create another matrix having the vectors and then multiply it. That's all. So here we created the matrix of angles of various corners, right? And that's all is required after for multiplication. And after multiplication, the shape gets shifted. So you can visualize the two matrix multiplications as basically matrix rotation. Sorry, the image rotation. Okay, the matrix multiplication provide there are many other linear transformations that are possible with matrix multiplication. One such is solving concurrent equation that we discussed earlier, and so on. So we'll continue from here tomorrow. Tomorrow we are going to start with the end-to-end project. The class will be at the same time what it is now. We can skip a lot of linear algebra from now onwards, and we can directly jump into the code. Have a good day. Bye-bye.